These demonstrate Thevenin's theorem, which states that any combination of voltage sources, current sources, and resistors can be reduced to a single voltage source and a single resistor. So, the scary-looking circuit on top can be reduced to the equivalent circuit on the bottom. Types. Thevenin theorem. Thevenin's theorem states that any complicated network across its load terminals can be substituted by a voltage source with one resistance in series. This theorem helps in the study of the variation of current in a particular branch when the resistance of the branch is varied while the remaining network remains the same. For example, in designing electrical and electronic circuits. A more general statement of Thevenin's theorem is that any linear active network consisting of independent or dependent voltage and current source and the network elements can be replaced by an equivalent circuit having a voltage source in series with a resistance, where the voltage source being the open circuit voltage across the open circuit load terminals and the resistance being the internal resistance of the source. In other words, the current flowing through a resistor connected across any two terminals of a network by an equivalent circuit having a voltage source ETH in series with a resistor RTH, where ETH is the open circuit voltage between the required two terminals called the Thevenin voltage and the RTH is the equivalent resistance of the network as seen from the two terminal with all other sources replaced by their internal resistances called Thevenin resistance. Extension of Thevenin's theorem. The Thevenin statement is explained with the help of a circuit shown below. Let us consider a simple DC circuit as shown in the figure above, where we have to find the load current IL by the Thevenin's theorem. In order to find the equivalent voltage source, RL is removed from the circuit as shown in the figure below and VOC or VTH is calculated. Now, to find the internal resistance of the network, Thevenin's resistance or equivalent resistance, in series with the open circuit voltage VOC, also known as Thevenin's voltage VTH, the voltage source is removed or we can say it is deactivated by a short circuit, as the source does not have any internal resistance, as shown in the figure below. Therefore, as per Thevenin's statement, the load current is determined by the circuit shown above and the equivalent Thevenin circuit is obtained. The load current IL is given as where VTH is the Thevenin's equivalent voltage. It is an open circuit voltage across the terminal of known as load terminal. RTH is the Thevenin's equivalent resistance, as seen from the load terminals where all the sources are replaced by their internal impedance. RL is the load resistance. Steps for solving Thevenin's theorem. Step 1, first of all remove the load resistance RL of the given circuit. Step 2, replace all the sources by their internal resistance. Step 3, if sources are ideal then short circuit the voltage source and open circuit the current source. Step 4, now find the equivalent resistance at the load terminals, known as Thevenin's resistance, RTH. Step 5, draw the Thevenin's equivalent circuit by connecting the load resistance and after that determine the desired response. This theorem is possibly the most extensively used networks theorem. It is applicable where it is desired to determine the current through or voltage across any one element in a network. Thevenin's theorem is an easy way to solve a complicated network. Again, in theorem, any combination of batteries and resistances with two terminals can be replaced by a single voltage source E and a single series resistor R. The value of E is the open circuit voltage at the terminals, and the value of R is E divided by the current with the terminals short circuit. The voltage. The Thevenin voltage E used in Thevenin's theorem is an ideal voltage source equal to the open circuit voltage at the terminals. In the example shows the resistance R2 does not affect this voltage and the resistances R1 and R3 form a voltage divider, giving Thevenin Norton resistance. The Thevenin resistance R used in Thevenin's theorem is the resistance measured at terminals AB with all voltage sources replaced by short circuits and all current sources replaced by open circuits. It can also be calculated by dividing the open circuit voltage by the short circuit current at AB, but the previous method is usually preferable and gives the same resistance is used in the Norton equivalent. The example replacing a network by its Thevenin equivalent can simplify the analysis of a complex circuit. In this example, The Thevenin voltage is just the output of the voltage divider formed by R1 and R3. The Thevenin resistance is the resistance looking back from A to B with voltage V1 replaced by a short circuit.